Okay, in your book now, we're looking at 7.3. 7.3, sorry, is going to be a little bit of a review of stuff we've already done. It's going to be using formula units. A little bit of review, a little bit of new stuff, which maybe is a nice place to go. So we're using our formula units. So formula units, if you'll remember, well, we have our formula. We have our ionic compound. Just as a little review, this is sodium. Sodium here is bonded to sulfide. And that's my name again. There's no Roman numeral because it's sodium. It's in our first row, so we know it's a +1. Sulfide because it's sulfur as an anion, single element ion, IDE. Now, if we look at what the compound is telling us that there's 2 atoms of sodium and 1 atom of sulfur. So if we want to add up its formula mass, like we've done before, we'd take that number and we'd multiply it by its atomic mass. Again, those atomic masses are right from the periodic table. We're never going to have to memorize them. So if we note sodium, we'd look up here and we see it's 22.99. Again, normally we'll cut them off at the hundredths place. We'll look up sulfur here. It is, put in that little circle, 32.065 or 32.07 very often is what we use. And notice that's what they have written down here. So we'd multiply 2 by that, we get our total. Get our total for sulfur, we add it up. This is the formula mass for the compound. So we've done that before. Again, if we just are thinking of it as atoms, well then this number is in atomic mass units. But if we talk about as a molar mass and look at it in units of grams per mole, then that becomes a molar mass. We change these units to grams per mole. So let's look at one more of these that might be a little bit more difficult, just as a review before we start doing some new stuff. So this is the formula mass of aluminum sulfate. Again, aluminum sulfate, this is sulfate, the polyatomic ion. Notice in it there are 2 aluminum atoms. There are 3 sulfur, because the sulfur is in parentheses with a 3 outside. And there's 12 oxygens, because there's 3 sets of 4. So there's 3 sulfates coordinated around every 2 aluminum. So there's actually 2 aluminums and 3 sulfates around them. So there's a total of 4, 8, 12 oxygen atoms. Well, again, we look up their masses on the periodic table. Notice they rounded these to the 10th instead of the 100th. That's okay. If we look at different examples, they're going to do that a little bit differently. I'm going to tell you to go to the 100th. Most of our test questions are going to be to the 100th. This example, they only went to the 10th, so the numbers are a little bit different. So the process is the same. Number multiplied by its mass from the periodic table. Number by its mass, number by its mass. We get a big mass, again, in atomic mass units. So this is a formula mass because it's in atomic mass units. If we want to look it up in molar masses, really all we do is change the units to grams per mole. Now we'd call it a molar mass. So our name would change just slightly depending on how we are using it. Really, the formula mass is only good if we want to know the mass of it. If we want to do anything with it, well, then we have to talk about it in units of grams per mole like we have done before. So here's our periodic table. Okay, now we want to do something with these. And we've done a little bit of this before, but we're going to expand upon it here. So now we are adding up the molar mass of calcium carbonate. So this is calcium carbonate. Notice calcium has a mass of 40. If we look at the periodic table, now they're rounding these off to the ones place. So just so you're aware where these numbers are coming from, calcium's actually like 40.0 something, but carbon, 12.01, they rounded off at 12. Oxygen is 15.9994, they rounded off at 16. Notice they're just multiplying it by the numbers in the formula. If we can't see the formula, I can increase it there a little bit. There's 3 oxygens in calcium carbonate. So we have 40 plus 12 plus 48, the product of 3 times 16. So the total mass of our calcium carbonate is 100 grams. And I don't really like the way they write it here. Really, it's 100 grams in every 1 mole of calcium carbonate. So we have our mass per mole. That is our formula mass. Now, notice it says if you have a mass of 25, how many moles do you have? Well, again, something we've done before. We take what we know, what we have, our 25 grams of calcium carbonate, and again, this might be a little bit of a review, and that's okay. 25 grams of calcium carbonate. Now, we want to get rid of grams, so I'm going to put my 100 grams of calcium carbonate on the bottom, and that 100 grams, again, is coming from adding up the masses on the periodic table. The 1 mole goes on top. That is 1 mole of calcium carbonate. Notice when I solve, grams of calcium carbonate cancel with grams of calcium carbonate. I have 25 times 1 divided by 100. Well, that's about 0.25 moles of calcium carbonate. So we can find the formula mass. We're going to find the molar mass. We can use it to solve for moles. So I'm going to keep working with that calcium carbonate example. So we already added up the molar mass. So it was 100 grams per mole. And we said that if we had 25 grams, we already solved that. If we had 25 grams of calcium carbonate, we said that it was 0.25 moles of calcium carbonate. Well, now let's ask ourselves, how many molecules are in that? So let's go that one step further. How many molecules of calcium carbonate are in this 25 grams? Well, remember, if I have that mass of 25 grams of calcium carbonate, if I think back to doing mole ratios, remember what we have to do is we have to convert this into moles first. So I still have to do what we just did here. I have to convert this into moles before I really can do anything else with it. So I'm going to divide by 100 grams of calcium carbonate again, over 1 mole. So it looks like, actually, if I wanted to solve for molecules, I could have just started with my mole value. That might have been easier. But oh well, we're there. So we divided by grams of calcium carbonate, grams of calcium carbonate. We have moles. Now, we have moles. What do we remember is our ratio to get from moles to molecules? Well, if we remember what 1 mole is, it is 6.02 times 10 to the 23rd. Anything we want, in this case, molecules. So that's going to give me molecules. Since that value is that big number of molecules, I'm going to put my 6.02 times 10 to the 23rd on top, molecules again, and my 1 mole on the bottom. And this, of course, is of my calcium carbonate. Now notice when we do the math, the 1 mole of calcium carbonate is going to cancel with the 1 mole of calcium carbonate. We'll have 25 divided by 100, that's 0.25, like we already had. 0.25 of 6.02 is approximately, what, 1 something? That is going to give me an answer of 1.5. Oh, and there's the bell. 1.5 times 10 to the 23rd molecules. Okay, so a bit of a review. I know we've done these before. We're going to be asked to do them again here. What is a little bit new is they're also going to have us look at percent compositions in this unit. So we want to look at how to calculate a percent composition of a compound. So maybe we should go back, take one of those compounds we were working on before. So I'm going to use my calcium carbonate. And we could have a calculation where they want us to look at the percent composition of the elements in calcium carbonate. So what's in calcium carbonate? Well, there's calcium, there's carbon, and there's oxygen. So we'd look at what is the percentage of each element in this. And we do the percent composition, we do it by mass. How we do the calculation is we look at the mass that is calcium, in this case 40 grams, and we divide it by the total mass of the compound, the 100 grams when we add it all up. So 40 divided by 100, well, that's pretty easy. It's 40%. Now I multiplied it by 100, 40% calcium. Let's do the carbon. So we have 12 divided by 100. Oh, this example is so, I shouldn't have picked such an easy example for myself. 12% carbon by mass. And for the oxygen, now we can't, be careful here, we have to take the total mass of oxygen in the compound, not just the mass of a single oxygen. So we have 48 divided by 100 times 100 to make it a percent. We have 48% oxygen. So this is a percent composition of our calcium carbonate. Now notice if we add these up, 0 plus 2 plus 8 is 0. Carry the 1, I get 100%. So percent compositions are nice and easy because if we do them, we know we can also check our answer by adding up all the elements at the end, and we should get a total of 100. Since we have all the numbers for our sodium sulfide, let's try that again. Let's see if we can't find the percent by mass of sodium and the percent by mass of sulfur in this compound. Well, for sodium, notice the total mass of sodium in the compound, not just the mass of a single one, but since there's two, we need to take the total mass of sodium in the compound is 45.98. We'll divide that by its total mass of 78.05. Bell again. Ooh, that's very interesting. 45.98 divided by 78.05, and we get, you can hear the buttons calculating in the distance, 58.9%. So it's 58.9% sulfur. Now, to solve for my sulfur, 32.07 divided by the total mass again, 78.05 times 100 to make it a percent. and I get 41.1%. Add those up, and a good check, we do get 100% as the total. So we can find, so the steps to find our percent composition is first, we need to know that total formula mass. Then we need to know the mass of each individual element. The mass of the element divided by the total mass, that is going to give us the percent composition of each element in the compound. Thank you, Bell. So here's a common problem we might have. We might have a problem where we have a compound that we want to use in lab called copper sulfate. But that copper sulfate, if it's exposed to air, sucks up, well, it sucks up probably is not the most appropriate term to describe it, but it orientates itself with water. It's called a hydrate. The water will stick to the compound. So this would be copper sulfate. The 5-pentahydrate would be the name because it coordinates with 5 water molecules. Now, before we use this compound in lab, we might want to dry it. So we might want to remove the amount of water. So we might be asked, what is the percent by mass of water in the copper sulfate pentahydrate? Well, just like a normal percent composition, we have to add up the gram formula mass of the structure. So sulfur is 32, copper, and that's right, in different colors, 63.55, while round sulfur off to the same, 32.07, and oxygens are 15.99 or 16.00. So I'm going to add the mass of our copper sulfate here. So there's 4 oxygens. I'm going to have to multiply that by 4. My total mass is 159.59. Now, to that, because this is only the mass of the copper sulfate, that really is all I want. The mass of the water piece is, well, like we'd find the normal mass. So first we'd add up the mass of the water. Hydrogen is 1 times 2, so 1.0079 times 2. And we'd add to it the 16 for water. That would be 18. We'll times that by 5 because there's 5 waters. So that's how we do a hydrate, is we multiply the mass of water by the number of waters that coordinate to the compound. So we'd get a total mass of 90. So 90 plus 159.59. We get a total mass of 249.59 grams per mole. Now, if we want to know the percent of that, that's water. The percent that's water would be, again, the mass of water, the 90 grams per mole, divided by the total mass of the compound, the 249.59 grams per mole. So finding the percent of water, we take the mass, which is water, which we solved right here. We divide that by the total, which is right here. And we find a percent. Obviously, at the end, we'll have to multiply it by 100. The percent is about 36.06%. So if we're trying to dry this compound, we can dry it until it goes down 36%, and then we'll know our compound is dry or fairly dry. So we can estimate when we've actually heated off and evaporated enough water so that we do have a dry compound to work with in our chemical reaction. Another place we use percent compositions. Pretend we have iron oxide. Okay, so we have some hematite. So we have an ore body, and we want to extract the iron, right? So our iron, normally when they mine iron, you don't mine and just find iron nuggets in the ground. It is bonded to oxygen, typically as hematite, as iron oxide, or some variation. We'll use iron oxide and just assume it's pure iron oxide just to make this a little bit simpler. So say we mine and we find some extremely large amount, 10,000 kilograms of our iron oxide. So we have 10,000 kilograms of iron oxide. What somebody might ask is, okay, after we refine this, how much pure iron can we extract out of this 10,000 kilograms of iron oxide? Well, an easy way to do it would be to say, well, what percent of iron oxide is iron? So we'd add up the mass of these pieces. Again, oxygen is 16. We'd multiply that by 3. Again, we'd probably carry the place out if we were doing this to actually extract iron. Iron is 55.85. We'd multiply that by 2. So add these pieces together. We have the total mass of the structure is 159.7 grams per mole. So that is our formula mass, our molar mass of iron oxide. So how much iron then can we extract from this 10,000 kilogram sample that we extracted? Well, what percent again of this is iron? Well, we take the mass of the piece that is iron, the 55.85, but again, we'd have to take the total amount that's iron, times 2, divide that by this total mass, 159.7, and multiply it by 100, and what do we get? We get that our sample is 69.94% iron. That is what our sample is. Our sample is 69.94% iron. So out of this 10,000 kilograms, there is a bit of waste, but if we take that 10,000 kilograms and we multiply it by this fraction that's iron, 69.94, again I'll divide it by 100 to change it back into a fraction, I can find how many kilograms of iron we can extract out of a 10,000 kilogram iron oxide sample, which in this case would be, what would it be? Cross out my zeros and I get 6,994 kilograms of iron. So even though this is a simplistic view of it, hopefully you can see the importance of doing this, especially in mining. If we're mining and we're getting these ores out of the ground, well, we want to know if there's a viable amount of ore in there to mine. So we have to look at what are the chemical compounds that is there, what percent is the metal we'd want, and really is there enough of it to be viable. So kind of a simplistic notion of why we want percent compositions, what types of problems they can help us solve. Goodbye. Sleep